Okay, good evening. In order to be sure we are on track with what we are doing, I think it is necessary that we check our um, our syllabus and look at how far we are faring. So far, so good. Measurement and units has been discussed. I could remember we talked about 7 fundamental quantities and their measurements and their units. Mass, time, we talked about fundamental quantities, we talked about derived quantities and units also. And then the issue of dimension was actually dealt with. I could remember I said that dimension is just represent the unit of some 3 fundamental quantities in a very unique way in terms of mass, length, and time. Any derived unit that you can represent in terms of mass, length, and time. That unit or that quantity can be represented. The dimension is what we call, is what we refer to as the dimension of the unit. Okay. Then limitations of experimental measurements as accuracy of instruments, estimation errors, significant figure standard forms. Those ones are actually the mathematical aspect of it that we should be well aware of, definitely. Then we have discussed measurement of positions, distance, displacement. We have discussed velocity. We have discussed acceleration. We have discussed vertical acceleration, linear acceleration. Okay. All of that are the things that catapult us to different motions, circular motions, and all of that. And then, of course, scalars and vectors. Scalars are quantities that have a particular unit of measurement in one variable, while vectors have a unit of measurement in 2 variables. So for scalar, it is just sizes, and for vector, is both size and direction. So another word for size is magnitude. So you can say it's both magnitude and direction, or simply magnitude. Another word for magnitude is size, so that it will be clear to everyone. Okay. So you are to resolve vectors in 2 variables. Now, this resolving of vector into perpendicular components will be dealt with when we get to vector itself, because there is a topic under this that we will talk about vectors. All right. We are going to delve into that properly. To resolve it, majorly here, you are going to just make use of the Pythagoras theorem rule, which is very straightforward too. I could tell you that physics is relatively mathematical. So if you are very good in physics, your mathematics won't be difficult. And if you are as well good in mathematics, your physics won't be difficult. So please pay attention to how we progress on that. Okay. So now under motion, what we need to do here now that we are here to cover is to discuss the laws of motion. Laws of motion. We've discussed the 4 types of motion. We've discussed the application of linear motion, vertical, and all of that. We've discussed different equations, but there are laws that are yet to be discussed according to this now. Before we now start moving into projectiles, these are Newton's law of motions, all right? And you see, there is an interwoven situation that we have here. When we talked about types of motion, relative motion, and causes of motion, in these causes of motion, we know that motion is caused when there is movement, when there is a force, imbalanced force, and that leads us to second law of motion. So we are going to discuss what causes motion majorly under the laws of motion. Probably I can just use these few minutes that I have to discuss these laws of motion. And once we are able to discuss that, we can look at projectiles. I think we are still on course. We are still very much on course. So it's just that we have not finished everything under motion. I think to this point, as of last week, I could remember we were solving questions on basically linear motions, and we were able to touch on some things, including the graph, including instantaneous velocity, acceleration, retardation, time factor, all those. So all the equations of motion have been dealt with up to that moment. All right. So tonight, I think it would be nice that we just quickly talk about which one should I go to? Let me see how much of time I have left. Okay, good. So let me just quickly give you an insight to this. So we'll work on the calculations on it too. I'm going to rush through the projectile, and I'm going to also talk about the Newton's law of motion by God's grace. So if we're able to deal with that tonight in few minutes that we have, then by God's grace, next class we'll do the calculations, then we will now go to motion in a circle. I think we are doing well. Then before we move to gravitational field, equilibrium of forces. Okay, so we are still on course. We are still very much on course. All right. So let me pull down this. Okay, so I want to share my whiteboard now. So we want to talk about, I don't want this. Okay, so we want to talk about projectile motion. Projectile motion. Let me write it well. Projectile motion. Okay, now so a projectile motion is a motion that behaves in this way. A projectile motion is a motion that behaves in this way. You know, it rises as it moves along, and then at some point it will begin to fall down until it gets back to the ground. It rises up, and then it moves as it moves along an horizontal plane. This is not a velocity time graph. This is on both sides, it is distance. This one is horizontal distance, HD, while this one is vertical distance, VD. VD. So it is not about velocity against time or displacement against time. This is both movement in two directions. Movement in two directions. However, and I need you to pay attention to this, however, there is a way we now represent this movement in terms of the time taken, neglecting horizontal distance covered. At some point, in this case now, when you have h for height, we can have t here. We are going to be discussing something, and this is what we'll be doing next week. The time it takes to reach the highest distance, we're going to find out, okay? Let me call it t, small letter t, while this one will represent the total time it takes to fly or to move through the whole trajectory, okay? An object that is undergoing these curvy types of motion is called a projectile. It's called a projectile. So the motion of the projectile is what we refer to as projectile motion. And of course, example is when you play a table tennis ball. When you are playing a table tennis ball, it's undergoing a kind of projectile motion. When you slap it, you know, it goes to the other side, jumping over the net on the table tennis. And that's how projectile motion occurs, all right? When you throw a stone at somebody, or you are trying to, like the story we were told years back, a stone. So it is whichever point the stone lands, that is the place the land will extend to. Not like this day that you have to measure it in meter square or something. that we buy. But, and if you throw a stone to a particular point, you see that it undergoes a kind of projectile motion. It will rise up as it is covering an horizontal distance, then it will begin to descend, just like what we have here. So that's what we call projectile motion, okay? All right. We can describe this particular direction as a kind of hyperbola, shape, a kind of hyperbola shape that you have here, okay? So that is how a projectile motion works. What are the things we are going to find out about projectile motion? We are going to be talking about t, small letter t, the time it takes to reach the maximum height, which is u sine t, u sine theta, okay, over g, and then the time to complete the whole journey, and that is 2u sine theta over g. All right. We are going to explain what all this means. When you want to derive this, you are going to derive this equation using the second law of motion. I mean, second equation rather, not law now. Second equation of motion. And you remember the second equation of motion says, I don't know, let me see, I would have loved to engage you, but don't worry, let's just continue. The second equation of motion says, V is equal to U plus AT. This is the second equation of motion. And you know that in this situation now, when you are throwing something up like this, and I want you to focus, the U that you have here is the initial velocity. But you can see that this velocity is neither vertical nor horizontal. It is oblique. So what is this sine theta doing? And that is just what I want to explain now. The sine theta is talking about the angle of projection. That is the theta. The angle of projection is the theta. And while your g is referred to as acceleration due to gravity. Now, you will now understand that as this projectile is moving up, it will get to a point which I call the maximum height, where the object will momentarily stop and then will begin to move again downwards. And the very important thing we need to note is that the time it takes to get here is the same time it will take to go back down to the horizontal place where it was projected. So we are calculating two things. So I call this one T1, I call this one T2, and fortunately for us, T1 will always be equal to T2. Yes, so that by the time you see this equation I wrote up here, you will understand why this 2 is coming to it. The small letter t is the time it takes to reach the maximum height. Capital letter T is the time it takes to reach the maximum height and the time it takes from that maximum height to reach the ground back. So and I've just shown you here that it will take the same time on both sides. So if it takes 5 seconds to get to the maximum height, from that maximum height down to the horizontal ground, it will also take 5 seconds. So it is very easy for us to say, okay, just multiply it by 2. And that is how we are able to get this capital letter T, which is what we call total time of flight. Total time of flight is called the capital letter T. And like I said, it is derived from the second equation of motion. So I can show you how that is done so that we can quickly move on. Don't forget, JAMB will not ask you to prove anything because it's not a theory question. But all of this must have been taught in your secondary school. So we are doing a bit of what I can call it now. We are doing a bit of refreshing the idea that you all have. So here, from V is equal to U plus AT, we can establish this. We say that because it is starting from somewhere, Initial velocity will be given, final velocity will be 0. So you have u plus, and don't forget it is going up. So the acceleration due to gravity will now become minus because it is going up. It is going up, so it will be minus gt. Now, the initial velocity given can come out here. So I can write this one as minus u is equal to minus gt. And then, like I said, you notice that the angle of projection is given. So when we want to find out the angle of projection, we instead of use the negative can cancel out first. So we instead of writing ordinary u, we write u sine theta. U sine theta, where theta is the angle of projection, and that will be equal to gt. So from here we can divide both sides by g, and that's how we got our answer to say our t is equal to u sine theta over g. So this is the formula for calculating the time to reach the maximum height. The formula for calculating the time to reach the maximum height. And then we also have the time of flight. Just multiply this by 2. The total time of flight will now be 2 times all of this, which is 2u sine theta all over g. So this one is called the time of flight. It is called the time of flight. All right, so keep this. Then the next thing we want to calculate, the height. The height. If you want to calculate the height, you will remember, should we calculate height first or range? Anyone, 2 right hand. Okay, let's calculate range. Let's calculate the range. Range S is equal to ut plus half at squared. This is the third equation of motion. This is the third equation of motion. So the range, we want to calculate the range. Don't forget that it is going up. Use sine theta multiply by t. All right. We now say, so I'll call it range. That is horizontal distance covered. But don't forget that when you are calculating the horizontal distance, something must have happened. And what is that has happened? We are going to have, look at what I want to write to. Initial velocity is 0. Is given, it's not 0. Initial velocity is given, all right? The time, the t here you have, because it is the range, the time it takes to cover the horizontal distance covered. So we will have it as, by the time you substitute u sine theta into bracket the t, then plus, because of space, or minus rather, it has to be plus anyway, plus half gt squared. It has to be, let me change this. I think something is not right here. Okay, plus 1 over 2 gt squared. Now, don't forget that it is horizontal. So there is something that will happen to us here. And that thing that will happen is that acceleration due to gravity will be 0 because it's not going up. We are calculating horizontal distance covered. So at that point, your g becomes 0. So all of this one automatically turn to 0. But for our t, we have a formula for t earlier stated. So I'm going to write it like r is equal to u sine theta into bracket another u sine theta now, sine theta over g. Yes, that's what I want to demonstrate. Or let me just use this like this, because I know this one is given. So I'm going to say u sine theta, then into bracket the value for t. We already have an equation for this already. We already have an equation for this, which is u sine theta over g. So I'm going to put it back, u sine theta over g. So by the time you multiply through, all right, so what you are going to have will now be u square sine square theta all over, because you are multiplying this, u square sine theta over g. That's what you do there. And all of this, by the time you find sine square theta, all of this one will give you some things that you need to put in. So at the end of the day, you have something like this, and I want you to pay attention to this. I want you to pay attention. This expansion will give us u square sine 2 theta over g by the time you do this. So this is the horizontal range. Now, there is something I want to bring out by giving you this. This is not, I've cut out some basic things, I've cut out some irrelevant things, but you need to know this. Now, this 2 theta, I need you to pay attention to this. Whenever theta is equal to 45 degrees, we say we have maximum range. Whenever theta is equal to 45 degrees, we have maximum range. When theta is equal to 45 degrees, 2 times 45 will give you 90, and sine 90 is 1. Sine 90 is 1. So at that point, you have your range to be u square over g. Sine 90 is 1. So maximum range, I will write it on the next slide. So Rm or R max will now be equal to u square over g. That is if theta is equal to 45 degrees for any projectile motion under any condition. When your theta angle of projection is 45 degrees, then you can bet that the maximum range will just be u square over g. So note that. And then the last one is the height covered. I just want to, so that next class will just be solving the height. The height will now be given as u square sine square theta over 2g. All right. So that is the formula. U square sine square theta over 2g. Now, so this is the maximum height. You can derive this equation from the fourth equation of motion that says that u square is equal to v square plus 2as. Is it v square is equal to u square plus 2? Okay, it's v square that's coming first, not u. So let me put it. V square is equal to u square plus 2as. So you can use this one. This is the fourth equation of motion. You can use this one to derive this equation I'm putting in red, this one. You can use this one to derive that, okay? So you have that. So I'm going to stop under projectile motion there. I'm trying to be very, very conscious of time, okay? Then what was the next thing I was about to discuss before I move on? Just a minute. Okay, that's for projectile motion given there. Okay, laws of motion, Newton's law. So let me quickly rush through Newton's laws for us. For Newton's law of motion, the first law says, Newton's law, let me just squeeze it here. Newton's laws. I don't understand this, my body, okay? I can still laws. Newton's laws. The first one says a body will contain or will continue in its state of motion or at the point of rest unless it is acted upon by an external or any unbalanced force. Okay, maybe we should not use the word external, but it's always good that it is the force will always be an unbalanced balanced force. If you park a car at one point, going, if you don't press brake or the car did not hit anything, the car will just continue to go straight like that. So two things, is either the body is resting or the body is moving in a place of continuous movement, unless another force is acting on
Excuse
it.
me, sir. Excuse me, sir.
Yes.
Please, can you re-explain the Newton's law?
Okay, so I'm just on number one. So pay attention again.
Okay.
So I said the first law, the first Newton's law of motion, the first one says a body will continue in its state of rest or in the state of linear acceleration unless it is acted upon by an unbalanced force. That's the law. People state it in different forms using different English. All right. If I stay in one point, I can remain stable there if nobody is pushing me, if anything is not happening to me. Do you get what I'm saying now? So, and if I'm walking straight, if I did not hit a wall or I'm not tired of walking straight, I can continue to walk straight for life unless something stops me. Probably I get tired. The force that is the energy with which I'm walking has depleted and I don't have any energy to walk again. Something must be responsible for my change in position or change of motion. That's what it's saying. So we have a consequence of that law. There's a consequence of that law. And the consequence of that law is called inertia. Inertia is, I want to define inertia now. Inertia is spelled I-N-E-R-T-I-A. Inertia. The consequence of the first law of Newton. The first law of Newton's motion. The first law. The consequence of that law is called inertia. That is, as a result of that law, there is something we are always observing. When objects are either moving or they are in a state of rest, that thing is called inertia. So I want to define inertia now. Inertia is the reluctance of a body to start motion if that body is in a place of rest or state of rest, or it's reluctant to stop moving if that body is in a state of uniform motion. I will come again. Inertia is the reluctance of a body to start moving if that body is in a state of rest, or its reluctance to stop moving if it is in a state of uniform motion. That's what they call inertia. Okay, and I'm going to give you an example. If a trailer is moving and it's moving very fast and then sees, a car that stopped suddenly, that trailer will not be able to stop immediately. Why? Because the force with which the trailer is moving cannot be stopped immediately. If you are driving a trailer and you want to stop, you must have started applying brakes several times before you get to where you need to stop, because of the consequence of inertia. Inertia itself depends on the mass. If a bicycle is running fast and you are stopping, the bicycle is not stopping, you can place your leg on the ground and then your leg will be dragging because the bicycle is not heavy. So you can stop it with your hand or with your leg. But a trailer cannot be stopped with an ordinary push or a hand. If a trailer is parked and you want to push it, you know how many people will surround that trailer to push it. But if it is an Okada, one person can just kick on the bike and push it and it will go. If it is a small car, the same thing. So the heavier an object is, the higher the inertia of that object. So the inertia of a 2-kilogram object will be lower than the inertia of a 200-kilogram object. So that is what we call inertia. Is a consequence of Newton's first law of motion. So let us note that. Second one, I think I will stop on this second one because my time is ticking fast. I will just define it like this. F is equal to MA. That's the second law of motion. The second law says the force that is acting on a body is directly proportional to the product of the mass of the body and the acceleration with which the body is moving. I come again. The force that is responsible for the motion of any object is directly proportional to the product of mass and acceleration of that body. So I've stated it. Anytime they ask you, state the second law of motion, and you write F is equal to ma. Physics, at least, this, they demand that you can just write it as F is equal to ma. It means you have to state it. What is F? F is force. M is mass. A is acceleration. That's it. That's it. That's it. I think I have 1 minute left. I can quickly state the third one. The third one says action and reaction are equal and opposite. Simple one. Action and reaction are equal and they are opposites. Note that action and reaction are equal and are opposite. We are always saying that. I could remember my first year in university when I was taking a course in physics. My lecturer said, if you hit your head against the wall, the way it pains you is the way it will pain the wall. The only difference is that you have neurons to measure the extent of pain, but wall doesn't have. But there is a way we can measure that extent when we talk about impact and the damage to the wall itself. It can just weaken the wall, it can just shake the wall, but if the wall is strong enough, you might not note that that is happening. But I want to stop on the second one. So we are going to pick it up from the from the third one when else we are meeting. So let me know, are you okay with all this for now? Suliat?
Yes. Yes, sir.
So Suliat, did you get that?
Yes, sir.
Okay, so let me stop here. We are going to meet by God's grace next class, and then we will start from the third law of motion. Thank you very much.
Okay, sir.
So the host can end the meeting here. It's 7.